Okay, so as we move on, we want to take a look at correlation coefficients that we might have to calculate. Just to remind you that correlation coefficients are on a spectrum from -1 through to +1. You can never have a correlation that's larger than 1. Now, if you remember back to GCSE and potentially Year 12 maths, when you were describing correlation, we were able to use qualitative descriptors. We were able to use strong positive, strong negative, weak positive, weak negative as a descriptor for our correlation. But we do want to get more specific. We want to be able to calculate our correlation coefficient, which will be a numerical value associated to the strength and parity of the correlation. So we do have a correlation coefficient spectrum, all of the possible values that we might get for a correlation coefficient, and that goes all the way from -1 to +1, but will never be outside of that range. Well, let's look at how your qualitative descriptors for correlation translate into numerical quantitative descriptors of correlation. If you did have a correlation coefficient that was 1, and also if it was -1, that would mean that all of the points of your data set, the points that you would plot on a scatter graph, would form an exact straight line. They would all be on that one straight line, not a little bit above or a little bit below, but exactly on the line. Why we refer to it as perfect correlation. We might have points that are very close to the line and they seem to form a relatively straight line, and we will refer to those values as strong correlation. They will take numerical values of anywhere in between 0.7 and 1 itself. We also have moderate correlation where, okay, there is some trend to the data, but they don't really fit snugly to the line, and we can take those as values from 0.5 to 0.7, and anything below that is either weak correlation or no correlation at all. So we would say that 0.5 to 0.3 would be weak correlation, but anything less than 0.3, as in between 0 and 0.3, we would say that there's no correlation. We can't really see any correlation in this case. This works exactly the same way for the negative values. So -1 is perfect correlation, perfect negative correlation, and in between -1 and -0.7 would be strong negative correlation. -0.7 to -0.5, that would be moderate negative correlation, and -0.5 to -0.3 would be weak negative correlation. Alright, so I've tried to color code this so you can get a picture in your head. It's a symmetrical spectrum of correlation coefficients with no correlation in this middle section and perfect correlation, strong correlation at the extremes. Well, let's match up these numerical descriptors with a diagram that would represent them. Well, here we have an example of, or a couple of examples of perfect correlation. These points are exactly in line with the line of best fit. They form a straight line. Every point lies on the line itself. Perfect correlation. Okay, so here they definitely form or seem to follow that line, but there are small deviations away from the line. So this would still be strong correlation. This is negative, well, strong negative correlation. Correlation coefficient of -0.8. Okay, these seem to form a positive correlation. They are trending in the right direction for positive correlation, but you can see that the deviations, the distance away from the actual line of best fit, from the regression line, is a lot larger. So this is a weaker correlation. This coefficient was 0.3. And here we obviously have no correlation. It would be very hard for me to determine whether these were moving in a positive correlated direction or a negative correlated direction. In fact, they just seem to not be either. I could probably draw a circle and they fit the pattern of the circle more than they fit the pattern of a straight line. Well, now that we know what type of values our correlation coefficient might take, and we have an idea of what the associated graph, the associated scatter graph might look like, let's take a look at an example question that will ask us to calculate a correlation coefficient. So it's not necessary to have a graph to be able to determine the type of correlation. So this question refers to the large data set, and it's referencing the daily mean wind speed and the daily maximum gust. Part A of the question is actually one that tests whether or not you're familiar with the large data set. We have NA in place of some of the data here. What does NA mean when referenced in the large data set? So these are the type of questions that will get you 1 or 2 marks just from being confident with that large data set. Well, NA meant that there was no data recorded for that particular date, or there was no data available for that particular date. I want you to be careful here. A lot of students then make the following assumption. They assume they can just use the value 0 instead. Well, that's not true, and that wouldn't be reasonable to make that assumption. The data was missing, not that the wind speed was 0, not that the gust was 0. So it will be inaccurate and irresponsible to make that assumption. There was a code in the large data set which was TR, which actually meant there was a trace amount. If I remember correctly, it was rainfall. There was a trace amount of rainfall, which meant there was a small amount, not enough to actually measure, and it was less than a specific value. And in that case, we were allowed to substitute 0, because it would make sense that we had such a small amount that we use 0. But that's very different from data being missing and instead choosing to use 0. Okay, not to get distracted too much, that's just one of the questions that they would regularly throw in with this topic, especially when you're looking at an excerpt from the large data set. Part B of the question asks us to calculate the product moment correlation coefficient. This is referred to regularly as the PMCC, the product moment correlation coefficient. We describe it with the letter R. Seems a bit strange that PMCC is described with the letter R, but actually a lot of the other abbreviated letter values are already taken up. P means something in maths, so does M, and so does C. So actually, maybe it does make sense to have R as the notation for the correlation coefficient. Okay, so in the wording of the question, we've been given a bit of a heads up. We've been given some extra information in the part where it says for the remaining 8 days. So we're not actually trying to calculate a correlation coefficient for all 10 days. It's the 2 days that have NA for their maximum gust value. The data we have in front of us is bivariate data. They come in pairs. We wouldn't be able to plot these onto a scatter graph if we only knew what one of the values were. We couldn't plot 4 for the mean wind speed and not know what the gust was. That there's nowhere to plot that on a coordinates axis. In a similar way, we can't use these values to calculate the correlation coefficient. So we need to have the understanding that these 2 pieces of data cannot be used. So these 2 days cannot be used in our correlation coefficient calculation. That leaves us with just 8 days, 8 pairs of data values to work with. Okay, so to calculate the PMCC, the R value, the numerical descriptor for the strength of the correlation, we're going to make use of one of our calculator functions. We looked at this last year, but I'll remind you that you're going to need to enter the data into list 1 and list 2 of the statistics menu. And when you're done from there, you're going to press calc, regression, X, A plus BX. Now the screen you get to there is going to display 5 variables. The 3 that are important are A, B, and R. R is the answer to this question. It's the correlation coefficient, in this case 0.9533. This has measured the strength of the correlation between those two variables. And this is very strong positive correlation between the maximum wind speed and the maximum gust. I'm going to go beyond the question here, just so I can show you what to do with the values of A and B. For this data set, A is 1.8478 and B is 2.5870. Well, these will form an equation of a straight line. If you remember, you pressed A plus BX, meaning that was the form of the equation of the regression line that you wanted to use. A is given to you on the screen, your y-intercept is 1.8478, and B is given to you on the screen, your gradient is 2.587. Let's just rewrite that in terms of G and W, and here we have our equation for the line of best fit, which we regularly refer to as the regression line, the linear regression line. The exam questions will refer to this as the linear regression line as well. So the examiners expect that you're familiar with that terminology and you know what we're referring to when we talk about the regression line. Don't forget, we can use the regression line to make predictions. We usually try to stick to interpolation to make sure that any predictions we make are within the confines of the data that we used to make the regression line. And we try to avoid using it to make a prediction, which would be extrapolation, meaning it's outside of the data that we used to generate the regression line. Okay, so all of this is available on that screen. A, B, and R. R is the coefficient. We're going to use that quite a lot in the rest of this topic that's coming up. And A and B are your intercept and your gradient. Okay, so let's just finish off this question here. It does say, with reference to your answer in part B, comment on the suitability of a linear regression line for this data. So we've been talking about that line of best fit. We've been talking about the linear regression line. How do we know whether or not it's suitable? Linear regression is only suitable when there is strong linear correlation. And now we found some very strong correlation. It was 0.95 or thereabouts, meaning that actually linear regression is appropriate for this data. It would make sense for us to try and make predictions from a straight line model, from a line of best fit, from the linear regression model for this data. Okay, so as I said before, this chapter, this topic, it is building on some of the concepts and understanding that you have from year 13 when we did come, that you have from GCSE and year 13 in terms of correlation and now regression. So practice some problems around correlation, linear regression, making predictions, interpolation and extrapolation, and whether or not a line is even suitable for a linear regression model by calculating the correlation coefficient.